Okay, good morning. Thank you for joining us today. We put up this event here to celebrate in our institute the 100 years of quantum mechanics. As you all know, we are really celebrating 100 years of Heisenberg and Schrödinger quantum mechanics. And because, of course, quantum mechanics began 25 years before. But we are also celebrating 100 years of Bose-Einstein condensation, or the proposal of Bose this year. And I think, as you know, this institute is the place of Bose-Einstein condensate in South America. And we take the opportunity also because one of the pioneers in atomic physics, Dan Kleppner, passed this year. And we use this opportunity to celebrate his life and work, because he was not only a pioneer in atomic physics, but also a seed for this place here at some point. So we start our 3 days, we start having done with us. I think it's the best way to honor his legacy, is to see what he had. So Vanderlei has a collection of recordings from done lectures, done interviews, and we are broadcasting this here 30 minutes each morning. And today, Dan is speaking about the history of atomic physics for the second half of last century. So, and his timeline is built with the Nobel Prizes. So from 1943, I think, to 2007, when the talk was recorded. Of course, many things happened from in the last 15 years, but this is the cut that he is talking about. Okay, so I think I am starting. And then after this, we have Bill Phillips talking to us about Bose-Einstein condensation. And then later, we come to local talks.
As Vanderlei explained, that I think both of us resonated to the idea of this school because it was the idea to reach out to a new community. So my working assumption was that the audience here was coming from another area, from the area of condensed matter physics. So that my lectures would start really at ground zero, teaching the most fundamental things. Now, this audience looks to me pretty sophisticated. It's hard to tell an atomic physicist just by looking at them, but I see quite a few here in the audience. And to them, I'll just have to apologize that I may be telling you things which are so elementary that they're not worth your attention. But at least it'll help to normalize the group. But before talking about that, since I am really addressing an audience from a different culture, I thought it'd be worth spending some time to sort of introduce you to the field of atomic physics, to explain how it got where it is today and where it is today. So this is a prelude, it's a digression. It's for your cultural enrichment. It is not going to help you professionally, except perhaps to inspire you when we see some of the achievements of the past and some of the things which have come out of those achievements. So what I want to do is to talk about atomic physics today and where it came from. Well, of course, it comes from the earliest roots of physics well, it would go back to even before the 18th century if one wishes, but I'm not going to go back quite that far. I would like to go back to where one can sort of see the roots of atomic physics as we know it right now. In the year 1900, atomic physics was essentially physics, that most, at least a large fraction of the papers which were published, if you had to classify them, you would classify them as atomic physics. But of course, in those days, which seem very romantic, looking back, one didn't distinguish between these different areas. It was all just physics. So what I want to do is to start back in 1923 and trace the development. It's a rather artificial way, but I think it's a pretty good way just by looking at the Nobel Prizes. I think this is perhaps justified because the Nobel Prizes are awarded for work which has major impact. And so we can see the steps which brought atomic physics to where it is today. But the Nobel Prizes, of course, don't cover all areas. Very few prizes are given. There are many great accomplishments. So it's rather sparse history, but it does nonetheless cover the highlights. And I realize I have left my laser pointer. All right, why start in 1923? Or actually, that was 1943 to 2005. I'm sorry, that was a misprint. I'd like it to start in 1943 because that when the prize was awarded to Otto Stern for the Stern-Gerlach experiment. As you recall, the Stern-Gerlach experiment was an experiment which proved the reality of spatial quantization using a molecular beam and deflecting the beam according to the magnetic sublevels the atom was in. That experiment had a revolutionary impact on the thinking about quantum mechanics at the time. Of course, this was before modern quantum theory was developed, but quantum ideas were very much in the air. And most people did not believe them. Max Planck did not believe them. Most of the community did not believe them. A young postdoc with Otto Stern was I. Rabi. And Rabi told me about the impact at the time, that it was electrifying to the physics community to actually see spatial quantization. It meant there was something physically real about the quantum ideas. So it had this electrifying effect in advancing the acceptance of quantum theory. It also advanced an important experimental technique, the experimental technique of molecular beams, and that plays a role in subsequent developments I want to talk about. Now, the work was done in 1923. The prize was given in 1943. It actually was awarded in 1944 because this was during the war, and it was not awarded in Stockholm. It was actually awarded in New York City, and both the prizes were actually awarded in the same ceremony. That Rabi got the prize for inventing molecular beam magnetic resonance. Now, the impact of that experimental discovery is really too vast to characterize because it underlies all of the developments in atomic physics since then, or at least most of them. It underlies the development of nuclear magnetic resonance. It underlies the development of the lasers, of optical pumping, of atom cooling, of Bose-Einstein condensation. So this work really was seminal. And one of the first major applications of the new resonance ideas was to nuclear magnetic resonance. And Bloch and Purcell received the Nobel Prize in 1952 for that discovery. It also had a profound effect on developing the application of these new resonance ideas to fundamental tests. Maybe the most fundamental question that was on the table in atomic physics at the time, or really physics in general. The Dirac theory was one of the great triumphs of quantum theory, the early developments of quantum theory, that many theorists consider Dirac's theory as the greatest theoretical accomplishment of the 20th century. But there were suspicions that the Dirac theory was not complete. And Willis Lamb actually proved this conclusively around 1948. It's an interesting concurrence of a new theoretical new theoretical developments where people were quite sure that there were problems with Dirac theory. But it also shows the importance of new experimental techniques. The underlying technique was the invention of magnetic resonance, but beyond that was the development of microwave methods in the radar projects during World War II. That technological development had huge implications for the advancement of science, and it's one of the interesting cases where one can see how new technology advances science. When we try to explain science to our friends, and particularly try to justify the expenditures on science to the funding agencies, one always stresses the great new technologies which come out of new science, and that's certainly true. But it works the other way around, and certainly the development of microwave techniques during World War II had a huge impact on the furthering of science. And one of those was that Willis Lamb had these techniques at his disposal. It was realized about that time in 1948, as soon as Lamb saw his results, it was realized that there were problems with the Dirac theory. And one of the implications of that was that the magnetic moment of the electron was not correctly given by the Dirac theory. That this was particularly pushed by a young protege of I.I. Rabi's there, who was Julian Stringer. And what they did was to push an experiment to measure the hyperfine separation of hydrogen, in which this effect would also take place. And Rabi actually carried out such an experiment. But they also designed an experiment, a molecular beams experiment, specifically to show that. And they did. And Cush shared in the Nobel Prize for showing that the magnetic moment of the electron was not given by the Dirac theory. Well, these ideas of resonance were spreading broadly. And resonance, of course, Rabi's first executed these ideas with magnetic resonance, molecular beam magnetic resonance, but the same ideas can be applied to other forms of interactions in atoms. And Charlie Towns was at Columbia University. Rabi was at Columbia University. There was a golden age of Columbia University. Rabi had a great instinct for choosing really smart people, and he had brought there, at first as a postdoc and then as a young faculty member, Charlie Towns. Towns was very interested in microwave spectroscopy for studying molecular structure, with a particular interest in looking for molecules in space. In the course of working on molecular and electric beam resonance, Towns hit upon the idea of the maser and started creating a maser at Columbia University. He does recount, he's written a very interesting autobiography. He does recount, though, how Rabi went into his lab one day and looked at the work and asked what he was doing, and Towns explained, and Rabi said, "Waste of time, why don't you do something more useful?" That just shows that Rabi was a great physicist, but he liked to make sweeping generalizations. Often they were right, sometimes they were wrong, and for young students, there is a moral in this. It is, of course, always good to speak to wise and experienced people and hear their opinions on things, but you mustn't always take them as gospel truth, because you can easily get talked out of doing good experiments. Well, if you're really good, you won't get talked out of doing a good experiment, and Towns was really good, and he carried on, and he invented the maser. And at the same time, there was great interest in the Soviet Union, and Basov and Prokhorov also worked on and created a maser. At the time, the incentive for making these masers was to make a better type of atomic clock. Rabi himself was the first person to propose the possibility of an atomic clock, but he never pursued it because he was interested in basic science and not in advancing technology. But out of this idea for the maser grew the idea of the laser, and by 1964 the laser had been demonstrated. Well, the next group that we have on here, Tominaga, Schwinger, and Feynman, would not normally classify themselves as atomic physicists. These were great theoretical physicists of great breadth, but as very young people, they had actually revised the Dirac theory, revised quantum electrodynamics, invented the theory of relativistic quantum electrodynamics, which is always trotted out as one of the greatest success stories in physics, because this theory is so accurate that it has been checked now to about a part in 10 to the 12th. And when one wants to make the claim that physics is a quantitative subject, there is no better example to use than this agreement between the predictions of quantum electrodynamics and the measurements to that precision. But beyond that, it is the model for modern relativistic, all modern field theories. Okay? So here again, we have an example of how something which started in physics to understand this discrepancy in the magnetic moment of the electron has had much broader implications for the advance of science. Alfred Kastler, really working by himself in Paris, starting as a high school teacher before the war, had been fascinated by the possibilities by polarized light. And he viewed polarized light not kind of as a wave phenomenon, but as a form in which you could transfer angular momentum into an atomic system. And working with his postdoc, Brossel, they actually executed that and showed that you could align the angular momentum of ground state atoms, and most of the angular momentum is in the spin of the nucleus. So you could put atoms into particular nuclear spin states through optical methods. Now, in retrospect, that was a very important step, although one didn't realize its significance at the time, because this was the first time that one could actually manipulate the internal states of atoms. Now, out of that ability came lots of useful experiments, new resonance techniques and such, and new types of atomic clocks. But in the history we're looking at today, it represents a major advance in atomic control. And there's also a very interesting sideline to that, that Jean Brossel, who was Kastler's postdoc, who had been actually sent to MIT to work with Francis Bitter, who was very well known for his work in developing high magnetic fields on this, had a correspondence with Kastler, and these ideas gradually emerged. And one of the very interesting things was that the first experiment to demonstrate optical pumping was actually sent to Kastler by Brossel. They were working very closely together on this. And we don't think of optical pumping particularly as an atomic beams method, but in fact their first experiments were. It came as a great discovery that you could align the nuclei of atoms in a gas which underwent many collisions, and the alignment would be preserved. That was just one of these bits of good fortune that no one really had thought about ahead of time. But when it came, it made these experiments much, much simpler, much more universal. And if there's a moral in that, is that sometimes things work out much better than you expect. Of course, not always. And I might say that I know that Kastler really was a wonderful person as a mentor to the scientific community, helped to reconstruct science in France after the war. Was always deeply regretful that Brossel did not share the Nobel Prize with him. Of course, he had no control over that. And Brossel himself seemed to take that in good stand. Okay, the next prize, it was to Nicola Bloembergen. These prizes were for 3 different topics altogether. Nicola Bloembergen really for inventing nonlinear optics. As he described it, he was at Harvard at the time. I was at Harvard University as a graduate student working with Norman Ramsey, and a number of these people were there. Purcell was there, Bloembergen was there, and of course, so was Ramsey. Bloembergen simply took the standard optical text, Born and Wolf, said he went through it and made all the linear terms nonlinear, and so what happened? Well, that's kind of oversimplifying it, but of course nonlinear optics has had major technological implications, and it also sort of opened new areas of spectroscopy and of optics. basically started a new optics. Shallow got the Nobel Prize for the advances in laser spectroscopy, saturation spectroscopy. This is the technique which made laser spectroscopy very practical for looking at atoms which were moving around very rapidly. This work certainly took place in his laboratory. My own interpretation of this is that the Nobel Committee really felt rather badly for not having Shallow share the Nobel Prize with Towns in the first place for the creation of the laser, and were sort of making amends. And certainly this work in his lab on saturation spectroscopy was of Nobel quality. But the chief scientist who did that was actually Ted Hench, who went to work with Shallow as a young postdoc and kind of revolutionized the field by making laser spectroscopy practical. So I feel that Ted kind of unfairly lost out on that one, but he's a very versatile person, and as you know, he has received the Nobel Prize. And K. Sigbahn got the prize for, I guess it's Kai Sigbahn, for electron scattering work, which was done. His father, also Mani Sigbahn, had gotten the Nobel Prize in much the same area. And I read just last week that K. Sigbahn has recently died. Well, the person I know best was Norman Ramsey, because he was my thesis advisor. And he got the Nobel Prize. He could have gotten it for so many things that they must have had difficulty making up their minds. But they awarded it to him for advances in high precision spectroscopy, what's called the Ramsey method, the double oscillatory field method, and its application to the hydrogen maser. Well, Ramsey did many other things. He started the search for parity non-conservation effects in atoms. He introduced the concepts of negative absolute temperatures. And of course, the Ramsey method itself has been enormously important. It's used in most atomic clocks, so it was quite appropriate that it be awarded. And they could have done, it's one of these awards which could have come 30 years earlier. Anyway, it was nice that it came then. I might say, though, that they slightly missed the boat on that. They talked about the separated oscillatory field method and its application to the hydrogen maser. Well, the hydrogen maser does not actually use that method, so they got the physics a little bit wrong on that. But I was happy they got it wrong, because as a graduate student and young postdoc, I worked with Norman on the invention of the hydrogen maser. So it's a pet project of mine. Demelt got the experiment, and he got the prize for measuring the magnetic moment of the electron more accurately than it had ever been done before, to about roughly a part in 10 to the 11th. Now, this provided a new precision test of QED, quantum electrodynamics. Quantum electrodynamics is doing very well. There is no reason right now to doubt its validity in the low energy region. Nonetheless, the ability to apply it and calculate it it's not an easy thing to do. It's a very demanding task. So this represented a new level in the agreement between theory and experiment. More importantly, though, Demelt had the vision to carry out experiments on one particle. He was the first person to carry out a precision measurement on a single electron. And the ability to measure single particles right now, to look at them and observe them, is a very important part of the arsenal of tools in atomic physics. And it's to Demelt that we have that vision. Powell invented the radio frequency ion trap. It's very closely associated with the techniques that Demelt used. It opens up new forms of mass spectroscopy, and ion trapping experiments today, of which there are quite a few, sort of owe their origins to this work of Powell. So now we come to the modern era, 1997 to 2005, and these were all centered, well, the first 6 were centered around the discovery of Bose-Einstein condensation. What made Bose-Einstein condensation possible was the creation of laser cooling methods. And these methods were developed by Steve Chu, Claude Cohn-Tanucci, and Bill Phillips. Others had been working on that too. They were not the only people in the field, but I think anyone looking at it objectively sees that what they did really led the field and moved it forwards. Eric Cornell, Wolfgang Ketterle, and Carl Wyman received it in 2001 for the discovery of Bose-Einstein condensation. When Bose-Einstein condensation was discovered, it made headlines around the world. Fortunately, the investigators were clever enough to label it Bose-Einstein condensation rather than quantum degeneracy in a quantum Bose gas. If you'd called it that, it would not have gotten into the newspapers at all. Degeneracy sounds slightly tawdry, but the important thing is that it's missing the magic name of Einstein, which properly belongs there. Now, it created great excitement and some skepticism about the level of excitement at the time. But the skepticism, I might say, came from the condensed matter theory, the condensed matter community, particularly the liquid helium community, who pointed out that Bose condensation was not new. It was known in liquid helium, and the atomic physicists are just terribly naive, and who they think they are anyway, stepping into our territory. Well, that was rather short-lived. It turns out that the phenomena is entirely different when viewed with these atomic quantum gases, and has led to many other new things. In any case, it caused a sensation then, and that sensation continues to today. The most recent prizes went, well, here's one prize to Roy Glauber, which again could have been given 30 years ago for the development of really the theory of quantum optics, the coherent field. His work had a huge impact in changing optics, bringing it into the 20th century, now the 21st century. And John Hall and Ted Hensch received it for the development of the optical frequency cone, a practical method for measuring the frequency of light. I know that had been a dream of Ted for many, many years, that the laser spectroscopy had gotten better and better, but it had outrun the possibilities of measurement, simply because previously one measured the wavelength of light very, very accurately, but that you can't do that to better than about a part in 10 to the 10th, and lasers could measure to much higher precision. But unless there was some way of knowing the frequency of the laser, the measurement was useless. There were techniques for measuring laser frequencies, but they were very laborious. Every measurement required basically a new laboratory. And then Ted had the vision of developing this general method which lets you measure easily the frequency of any light, and John Hall, who was an early expert in high precision laser spectroscopy, helped to implement that by making it more general. And that really is a revolutionary technology. Well, here we have within, this is 8 years, there are 9 Nobel Prizes in this field, which suggests that the field is really hopping. And in fact, the field really is hopping. But if one looks back altogether at these, 2 things emerged when I looked at them. The Nobel Prize is given because work has impact. You know, it isn't given for promise. It's given for work which has a visible impact on the field. So in each case, this work had a visible impact. But looking back on it, the impact was just much larger than people could have dreamt of at the time. So this is a very nice moral to see. If you like, it's a short-sightedness of scientists, even the best people in the world trying to decide who should get a Nobel Prize and doing their best to do it, that the reality of these dreams always exceeds the expectations at the time. That's a very nice quality about science. It's one of the areas, one of the activities in human affairs where things frequently work out much better than you could expect. Often things work out not as well as you can expect. You know, the slums do not go away, the wars do not stop. Society has a hard time organizing itself, no matter how well it tries. Things often don't work out as well as you'd hope. But in science, as a rule, things work out much better than you hope, some of the time. Now, a lot of things don't work, but the important thing is that enough things work to make the enterprise really a great enterprise. And I'd just like to briefly summarize where we are today in atomic physics. Okay. First topic, science and the basic laws of nature. Fundamental tests have always been a driving force in atomic physics, and they continue to be, and they're very closely allied with very interesting developments in technology, in metrology, in atomic clocks. And of course, the real success story for atomic physics, if you want to trot out, well, you should trot out the laser, but lots of people take credit for the laser. But these atomic clocks led to the global positioning system. But this question, is alpha constant or is it changing in time? There are applications to detection of gravitational waves. That's been a very long-term vision, but it's moving forward at seemingly quite a healthy pace. It develops the magnetometry and medical imaging and matter wave interferometry. These are just some of the new techniques which are being used to basic tests. Second thing is the subject of this conference, towards absolute zero. Condensed matter physics and dilute atomic systems. That's what this conference is all about, and that was sort of headlined in this report. You can tune the interactions between atoms, optical lattices, optics. These are some of the things that we'll be hearing about, and then applications into other areas of physics. Another very interesting area is extreme light, namely table source X-ray lasers, high-intensity X-rays, X-ray nonlinear optics, ultra-intense lasers. One application is accelerating particles with light. And now lasers have moved. Well, when I was just starting my career, people were starting to think about doing nanosecond physics, which seemed to me incredible. And then before too long, they were talking about picosecond physics, 10 to the minus 12 seconds, which seemed to me just unbelievable. And then they started talking about femtosecond physics, which seemed to me even more unbelievable. But now they're in the attosecond regime, and it just shows that that physics can move faster than one's imagination, at least this one's imagination. Okay? An old dream, quantum control of molecules, has not moved forward over the years, but now there's a feeling that you can, because of the great control one has over light with these new methods for controlling the phases and frequencies of light. And one of the applications there is this attosecond science. Photonics on the nano world, well, these are just atomic techniques which are useful in this world and are very appealing, particularly to politicians, since nanoscience is very, very fashionable. And then this quantum information with light and atoms. This is another area which has sort of grown more than people might have guessed. It's engaging some of some of the best theorists right now have moved into this field. It's endlessly fascinating, and there are lots of experiments going on. So far, the advances in theory have been outracing the advances in experiments, but there's a lot of interest in this, including in the CUA right now.
Okay, let's thank again Dan Kleppner and
then we'll not take questions, but if you have questions, Vanderlei is here also. We'll switch to Bill Phillips now live. I think Vanderlei, Bill, do you hear us? Okay, we still don't hear Bill.
Okay.
Okay, we hear you now. I think Vanderlei will introduce Bill.
It's a great pleasure for us to have Bill giving a talk in this commemoration. It's an event that we are organizing, mostly broadcast by internet. So many students are following, and I hope you keep following for the whole day different talks and everything. Bill is a friend of the house. He's also an honor professor in the University of São Paulo. And he is a former student of Dan Kleppner. He has been doing so many things that if I start to list the things that Bill has done, we're not going to end, right? We're going to spend more time explaining Bill's life than the talk he's going to give. But Bill is being a very nice follow of this whole development of the new area of atomic physics, which is a good application of quantum physics that we are celebrating, which is cold atoms. And he was the first one to demonstrate and actually tell us how to produce a slow beam of atoms. And from there is where everything starts. And along the many years, Bill has a lot of contributions. You know, when he put together the group in NIST, there was a big push for the development of trapping, for the development of condensation further on, and the applications that we have for condensation. As you know, we are this year, we are celebrating many things. You know, for physics, for physicists, in fact, we celebrate every moment quantum mechanics, right? Because we could not be doing what we do without quantum mechanics. But also the beginning of the quantum statistics was very important, not only for atomic physics, also to understand the condensed matter in general and many other things. And I think Bill today is going to give us a kind of taste about this whole thing about the quantum statistics. But Bill is also a very important guy in the development of high precision. You know, he always was an enthusiast of the atomic clocks. He worked himself with high precision. You know, he started his career at NIST trying to make sure that we could measure very well magnetic field, right, Bill? And then end by using magnetic field for helping to decelerate atoms and to trap. Well, without further delay, I want to give you the word to Bill, and I'm sure he's going to deliver a very nice talk. And unfortunately, we are not taking questions from the internet, otherwise this will take a little longer. But from the auditorium, we can take questions for Bill, if there is any at the end of the talk. Thank you very much, Bill, and it's a very pleasure to see you very well dressed and everything.
Well, thank you very much, Vanderlei. Now I'm going to try to share my screen and try to get everything the way it should be. Okay, now let's see. Okay, do you see my title slide? Okay, I'm not sure that I'm getting an indication that this is all right. Maybe.
Bill, we see the slide and we see you.
Excellent. Okay, so here we are celebrating a number of things. The 100th anniversary of quantum mechanics, the 30th anniversary of the achievement of Bose-Einstein condensation, and of course, a tribute to Dan Kleppner, who has had so much to do both with quantum mechanics and with Bose-Einstein condensation. So I've made the title of my talk, Satyendra Bose, Albert Einstein, and Dan Kleppner, The Birth of Quantum Statistics and the Beginnings of Bose-Einstein Condensation. I'm part of the Joint Quantum Institute, and I particularly want to highlight the other members of the Laser Cooling and Trapping Group, Ian Spielman, Trey Porto, Ida Tietzinga, Nicole Younger-Halpern, and Elena Green, as well as the retired members of the of the laser cooling and trapping group. And all these people have contributed a great deal to the things I'm going to be talking about today. I want to begin with a disclaimer to emphasize that I am not a historian of science, and I'm going to be telling you a lot about history, and I might not have it all right. People have told me stories about the history, and I'm going to be passing on some of these stories, but I have not done the kind of research that a true historian would do to be sure that all of these stories are true. And so I'm very happy to receive from you, along with your questions, any corrections and additions you may have to the history. So, as we've said a number of times today, the year 2025 is a significant anniversary year. 100 years of quantum mechanics, Heisenberg's seminal paper, which in a sense began what we now think of as being quantum mechanics, happened in this year. In addition, we have the work of de Broglie, the idea that particles can be treated as waves. The work of Dirac, who, based on Heisenberg's work, came up with what we now call the Heisenberg equation of motion in 1925. The work of Schrödinger, just 1 year later, giving us the Schrödinger equation based on de Broglie's wave ideas. So there are a lot of 100 or near 100-year anniversaries in this year of 2025, which is officially the International Year of Quantum Science and Technology as designated by UNESCO. And of course, 30 years ago, Bose-Einstein condensation was first achieved in an atomic gas, a dilute atomic gas, according to the ideas that Einstein had come up with. And a few years later, that work was recognized with a Nobel Prize. But also, 101 years ago, Bose invented quantum statistics. So this was a pretty important development. So what was it that happened with Bose and then the involvement of Einstein, and how did Bose-Einstein condensation come into being 100 years ago? Well, first there's a prologue, which includes some of the birth of quantum theory, but not yet of quantum mechanics, the kind of distinction we make of the way we understood quantum phenomena before Heisenberg, before Schrödinger. Things began with Planck. People had known for a very long time that when you heat things up enough, they glow. But nobody was able to calculate what the spectrum of the light coming from a glowing body was. Classically, people would calculate that as you go to shorter wavelengths, you get more and more light out. And this was certainly not the case. In fact, it was known that the spectrum had a peak that would change depending upon what the temperature of the black body was, but nobody was able to do a calculation to reproduce the experimentally known spectrum until Planck in the year 1900. And Planck used what he considered to be a mathematical trick. He made the assumption that when the black body, imagine a box, a black box held at a certain temperature, inside of which there's an electromagnetic field, and the electromagnetic field is exchanging energy with the box. And Planck made the assumption that when that energy was exchanged, that it was done in small chunks, which he called quanta. And the size of those quanta was, that is, the energy, was the frequency of the radiation times a new constant, which we now call Planck's constant. Now, Planck's constant is very small, but as the frequency increases, so does the energy, and it's this increase that prevents the so-called ultraviolet catastrophe that produced the wrong answer when one tried to understand this classically. But Planck, and I want to emphasize this, always thought of this as a calculational trick rather than as an indication of the nature of light itself. Einstein took Planck's idea further. He really saw radiation, electromagnetic radiation, as particles, which we now call photons, but it wasn't, that terminology didn't exist when Einstein first worked on it. But he thought of electromagnetic radiation as being a collection of photons, each of which had an energy equal to Planck's constant times the frequency. And using this idea, he was able to explain the photoelectric effect. And it was for this that he got the Nobel Prize. This was the beginning of what we now call wave-particle duality, something that people had well understood as being a wave, namely light and other forms of electromagnetic radiation. These were very firmly waves. The work of Maxwell experiments in the 19th century had established this very well. Einstein emphasizes that this is the case and says he's also going to think of these things as particles. Years later, Louis de Broglie completes this idea with his hypothesis about the wave nature of electrons and other particles, and that completed the idea of wave-particle duality. But it begins here with Einstein. Einstein continued this idea. He considers the momentum of photons. Dan Kleppner's lectures will talk some more about this. And Einstein showed how a gas of atoms could come to equilibrium with a gas of photons. And this, excuse me, introduced many of the ideas that underpin laser cooling, which has been so important in the achievement of Bose-Einstein condensation. So, 1924, Bose proposes a new way of deriving Planck's radiation law using statistical mechanics and using a new way of counting. Now, I want to remind you that statistical mechanics is based on the idea of counting how many different ways you can have a microscopic state that corresponds to a certain macroscopic state. In other words, imagine if you had a gas at a certain temperature and pressure, how many different ways could you arrange the atoms or molecules that make up that gas so as to produce that same temperature and pressure? And the more microscopic ways you can do that, the more likely it is that you're going to have that kind of a state. So counting the number of microscopic states is at the heart of statistical mechanics. And Bose was proposing a new way of doing that. Here's the beginning of that paper, as published in Zeitschrift für Physik. What was it that was different? What was the new thing that Bose brought to our understanding about how to count? That's the key thing. Bose had a new way of counting. Now, in order to demonstrate that for you, I'm going to stop sharing my screen, and I'm hoping that you can now see me on the big screen. Emmanuel, is that good? Can you see me on the big screen?
Yes, Bill, we see you very, very big.
Excellent. So let's imagine, I'm so sorry, too early in the morning for me here in Gaithersburg. Okay, let's imagine that we're in the 19th century, and particles are distinguishable. And I want to ask, so here's two particles that I think you can see are distinguishable, okay? Now, I want to ask how to count how many ways I can distribute these two particles so that, and the only thing I care about these particles is whether they're on this side or on this side, okay? Well, here's one way, okay? Here's another way. Okay, that's two. Here's a third way, and here's a fourth way. So there's four different ways that I can put these two particles on one side or the other. And of those ways, half of those ways have both particles on the same side. Now, let's imagine that the particles are not distinguishable. Now, this was not a concept that even existed in the 19th century, as far as I can tell. But let's imagine that they're indistinguishable. So here's one way. Now, you might think that that's another way, but it's not, because these particles are indistinguishable. So this state is no different from this state. So we've got one state here, then we've got another one here, and another one here. So there are three different ways that I can put two particles on the left or the right. And of those three ways, 2/3 of those ways have both particles on the same side. Now, this was the new idea, the new way of counting that Bose brought to physics. Particles that behave this way are now called bosons, because it was Bose who first described how they worked. And you've probably heard that bosons love to be together. This isn't because the bosons attract each other, it's because of the way we count. When these things are considered as bosons, then 2/3 of the ways that I've described put the two particles together. But if these particles are distinguishable, then only half of the ways put the particles together. So that's why bosons like to be together more than what I like to call bosons, that is, distinguishable particles that would follow the kind of counting statistics that Boltzmann described. Okay, now I'm going to try to go back to sharing my screen. Okay, am I good? Back to the
Yes, everything's good, Bill.
excellent. So, using this way of counting, Bose was able to use statistical mechanics to reproduce Planck's radiation formula. Now, there's some really interesting history that comes behind this this discovery by Bose. According to the legend, Bose was teaching a class in statistical mechanics, and he was showing his class that using statistical mechanics, you could not get the Planck radiation law. In other words, he was demonstrating for the class the difficulty that scientists in the early part of the century had with the spectrum of blackbody radiation. But in the process of doing the derivation for his class, he made a mistake, or what was thought of at the time as being a mistake. He counted wrong because he assumed in the class that the photons were indistinguishable and therefore counted wrong, and got, to his surprise, the Planck radiation law. So he wrote it up, and he submitted it to an English journal called Philosophical Magazine, and they promptly rejected the paper because it was obviously ridiculous. It went against everything that they understood about statistical mechanics, and they rejected the paper. So what Bose did was he took the paper and sent it to Einstein. What bravado, a young physicist like Bose, to send this to Einstein. Einstein read the paper and immediately recognized how revolutionary this was. Einstein translated the paper into German and submitted it to Zeitschrift für Physik, and because he was Einstein, they immediately published it. And here is the end of the paper, in which Einstein's translation in German. Now I'm translating it back into English. It says which equation is equivalent to Planck's formula. And then there's a translator's note. It says Bose's derivation of Planck's formula represents, in my opinion, an important advance. The method used here also provides the quantum theory of an ideal gas, which I shall explain elsewhere. So Einstein understood in ways that apparently most other people didn't, how important what Bose had done was, how important the idea of indistinguishability was. Boltzmann's way of counting implicitly assumed that particles were distinguishable, but Bose's way of counting assumed what we now consider to be a fundamental feature of quantum mechanics, the quantum mechanical indistinguishability, an entirely new idea. Now, it's not completely without precedent. People like Lord Kelvin, in talking about how you should develop standards of measurement, thought that atoms were the best way of doing this because he said that atoms were all completely identical in every property. Well, that was true, but it's not the same thing as indistinguishability for counting purposes. As far as I know, it was not until Bose that it was really understood that this changed the way you count. And so we might very well wonder how a genius like Kelvin knew that all sodium atoms were absolutely alike at a time when a lot of people didn't even believe in atoms. And we can also wonder what kind of innate genius inspired Bose to develop a new way of counting. And we might also be in awe of how Einstein knew what to do next, which was to apply the ideas of Bose to the theory of an ideal gas. And here is the paper, just days after the paper by Bose, which Einstein translated for Zeitschrift für Physik, appeared. Einstein has his theory of an ideal gas. And what did Einstein do with this new insight of Bose? What was in this new paper by Einstein? Well, he considered a gas of atoms. We would call them today bosons. And the key thing that's different about this gas of atoms compared to a gas of photons is that their number is conserved. If I have photons inside a box and I cool the box down, the number of photons in the box is going to go down. Whereas if I've got a box that has atoms in it, and those atoms can reflect off the surface, then the number of atoms stays the same. And what Einstein found was that following the statistics counting the way that Bose had originated, that as you have a box at a constant temperature and you add atoms to it and they come to the same temperature, that there comes a point where the distribution that you would calculate using Bose's ideas, in a sense, fills up. There's no more room for the next atom that you want to put in, and so that atom has to go into the lowest energy state, which for Einstein was a state of zero velocity. Today, understanding quantum mechanics and the uncertainty principle, we would say it's the lowest possible state of motion of the atom. But nevertheless, the point is that you get to a point where, as the density goes up, you get to the point where all the available states in non-zero velocities are filled up, and the additional atoms have to be at zero velocity. And it's that macroscopic number of atoms that are at zero velocity that we call today a Bose-Einstein condensate. Now, one of the things that I want to emphasize here is that Einstein is treating an ideal gas, and he's finding that there is a phase transition, something that happens at a particular density, at a particular temperature, where the nature of the gas changes. And the way in which it changes is that a macroscopic fraction of the atoms are not moving, according to Einstein, or are in the lowest energy state, as we would say today. This is a phase transition in an ideal gas. This is revolutionary. Up until this time, the kind of phase transitions that we're familiar with in a gas happen because the gas is not ideal. Steam condenses into water because the water molecules attract each other and stick together. If the gas is ideal, before Einstein, there is no such thing as a phase transition. If we cool it down, it's a gas all the way to absolute zero. Now, that never happens in real life because in real life, the constituents of a gas always interact. There are no ideal gases, but theoretically, Einstein showed that there was indeed a transition in an ideal gas. And here's the critical temperature. Now, I don't want to bore you with all the things that go into this critical temperature, but the key thing is that if the number density of the atoms is higher, the temperature is going to be higher. If the mass is lower, then the temperature is going to be higher. So if you want to see this phenomenon at some given temperature that is not yet cold enough, then you can add atoms, or you can use an atom that has a lower mass. Now, just to give you an idea of how difficult it's going to be to achieve this, if this were rubidium atoms, which is the atom in which it was first achieved in a near ideal gas, if the atoms had a density of 10 to the 14 atoms per cubic centimeter, which is hard to achieve, the critical temperature would be 300 nanokelvin, a temperature that had never been achieved until Bose-Einstein condensation was finally realized in 1995. By comparison, the density of air is more than 5 orders of magnitude higher. So this is a relatively low density, but a difficult one to achieve, and it would require an incredibly low temperature. So this is one of the reasons why it was so difficult and took so many years before it would be possible to achieve Bose-Einstein condensation. Now, there's another thing that I wanted to point out. Another way of thinking about the condition for Bose-Einstein condensation. All particles of matter have wave-like properties, as de Broglie had already pointed out, around that Bose-Einstein condensation happens when the atoms are spaced by about their de Broglie wavelength. This is when the atomic wave functions overlap and when the idea of indistinguishability actually matters. Now, as far as I know, Einstein didn't think about the problem this way, even though apparently he knew about de Broglie, which had been happening at about the same time. So it may be somewhat interesting why, if Einstein knew about de Broglie, why didn't he also think about it this way? But as far as I can tell, he didn't. Now, since we're also emphasizing Dan Kleppner, I think that it's a good idea right now if we stop and listen to what Dan had to say about Bose-Einstein condensation.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But
now, before I go on, I just want to make sure, is everyone hearing Dan?
Yes, Bill.
Excellent. Thank you. Let's keep going.
under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. If you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us. But in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one. It's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
So wonderful to have that that video from Dan. Okay, so so this sort of illustrates the same thing that Dan was showing so well in that little video clip. Another way of expressing this idea that the atoms are spaced by about the de Broglie wavelength is that the density times the cube of the de Broglie wavelength is about 1, and this quantity is what is sometimes called the phase space density, the quantum phase space density, and Bose condensation happens when the phase space density is approximately unity. Now, I want to make a few important points. Not all atoms are bosons. Many atoms are, but many are fermions. The other kind, the kind of particle that don't like to be together. Photons, which are bosons, don't Bose condense under normal conditions for the reasons that I've already mentioned, that the photon number is not conserved. And as the temperature goes down, which is what you would imagine you would do to get Bose condensation, so does the density, so you never achieve Bose condensation, or at least not under what we might call normal circumstances. Real atoms interact with each other, so typically something else happens before Bose-Einstein condensation happens. In fact, in the early days, when people were trying to get Bose condensation, some people speculated that it was some sort of a rule of nature, that we would never get Bose condensation because something else would always happen. But that's not true, fortunately. And furthermore, Einstein did not take into account the quantization of the motional states of the trapped gas, and that leads to a different perspective. Vanderlei Bagnato, who gave that very kind introduction, was one of the pioneers in describing, along with Dan Kleppner and Dave Pritchard, how trapping the atoms changes the way we think about Bose-Einstein condensation, and also how it affects changing the dimensionality of the problem. Now, I don't know. Please tell me whether it's possible to do this, but I'd be very happy to stop right now before going on with the rest of the talk and see if there are any questions. And in fact, I've got a list of possible questions that you might want to ask me in black, but I've also got a number of questions in blue that I'd like to ask you in case any of you know the history of these things better than I do. For example, how well did Bose understand how revolutionary his idea was? Is there any evidence that people like Maxwell and Boltzmann ever thought about indistinguishability? But you may want to ask me some of these other questions. But if this is too difficult to arrange right now, I can just go on. So tell me what I should do.
No, we can have questions from here. Vanderlei has a question.
Excellent.
Bill, very nice then. And it's very interesting that when the wave packet represented by the de Broglie wave overlap, we have the transition, more or less. If you take 1 divided by lambda cubic at that point, you more or less close it to the critical temperature. Now, we all know that phase transition is a compromise between enthalpy and entropy, right? If you take the free energy, you have enthalpy and entropy times the temperature, and when that start to be compensate each other, we have a normal phase transition, like Dan said, going from vapor to liquid and so on. My question to you is that crazy to think that when the wave... let me finish the question.
Yeah.
When the wave packets start to overlap, it's like creating a different type of compensation between enthalpy and entropy, and then the system now goes to a phase transition, which is the Bose condensation. And well, what do you think?
Well, I don't know. The answer is I don't know. I think that this is going to require the attention of somebody who understands thermodynamics better than I do. Now, thermodynamics was a real favorite of Einstein. So you sort of wonder whether he would have anything to say about this. Now, an interesting feature about Einstein is later in his life, he, in a sense, repented of this idea of Bose-Einstein condensation. He thought it was just too crazy to happen. So I'm not sure if that tells us anything, but I wish I knew the answer to your question. And maybe the next time we're in the same room, we can discuss it more. Or maybe there's somebody here in the audience who has a more mature understanding of thermodynamics than I do, who could comment.
Thank you, Bill. We have another question.
Hi, hello, Bill. This is Leandro here, Vanderlei student. And I have actually a curiosity, not like a question. But currently, how would you describe the stage of our field, which is the Bose-Einstein condensation? Is this a young field, or it became like a mature field? How would you describe that?
Yeah, so I think that I would say that the field is entering maturity. In other words, I think we're just perhaps at the end of being young, when every time you turn around, something new is going on, and beginning to enter the stage where lots of things are understood, and we can now use Bose condensates as a tool for doing other new kinds of physics. In other words, I think that today, as opposed to, say, 20 years ago, the emphasis was, what new things can we learn about condensates? Whereas today, I would say the emphasis is beginning to be, what new things can we learn with condensates?
Okay. I don't see further questions, Bill. So I think we might go on.
Great. So one of the questions about Bose condensation, and by the way, I should say, sometimes people seem to be confused about where the idea of Bose-Einstein condensation came from. The fact is that it comes from Einstein based on the idea of Bose. It is not a collaboration between Einstein and Bose, as some people have sometimes tried to suggest. It's entirely the invention of Einstein, but entirely motivated by the new way of counting that Bose came up with. But once we have it, we might ask ourselves, is there something that we already know about that that corresponds to it? Well, superconductivity had already been discovered back in 1911, but it was going to be a long time before anybody understood what superconductivity was about. Today, the modern understanding would be that superconductivity occurs when electrons pair up as Cooper pairs, not bound states, but correlated states of electrons that, in some sense, form with two electrons a boson, since the electrons are fermions. And that as soon as that pairing happens, at least in conventional superconductivity, as described by Bardeen, Cooper, and Schrieffer, that Bose condensation occurs, and superconductivity is a phenomenon of Bose condensation of pairs. But this is a very modern point of view, and certainly not something that people were thinking about at the time that Einstein came up with Bose condensation. Now, some years after Bose Einstein condensation was predicted by Einstein, we had the discovery of superfluid helium, and here you're looking at a vessel that has superfluid helium in it, and you notice that down here there's a droplet that's coming off the bottom of the vessel, and that's because the superfluid is crawling up the walls and then dripping down the sides. That's one of the phenomena associated with superfluidity, and people speculated as to whether this was related to Bose condensation, and I suppose it is. But one of the real problems is that it's not what Einstein was talking about. This is already a strongly interacting liquid that, if you cool it down even more, becomes a superfluid. It's not an ideal gas in any sense of the way that Einstein was considering, and so both of these phenomena were. There was speculation about whether this was evidence of Bose-Einstein condensation, but whatever it wasn't what Einstein had predicted. So now we come to the modern era. 1976. I was just finishing up my PhD with Dan Kleppner, and this paper by Swale and Nausenow appeared in Physical Review Letters. And what it suggested was that a gas of atomic hydrogen, where you align all the spins of the hydrogen, the electron spins of the hydrogen in the same direction using, say, a magnetic field, that this would be a nearly ideal gas that could undergo Bose-Einstein condensation and therefore be able to see this phenomena that Einstein had predicted so many years ago in pretty much the same way that Einstein had thought about it. In other words, this would avoid the kinds of complications that you had with liquid helium, or the very different situation you had in a superconductor. This would be doing what Einstein had imagined. Well, this was wonderful. Dan Kleppner knew a lot about hydrogen. He'd invented the hydrogen maser along with Norman Ramsey. I, for my thesis research, did a precision measurement using a high-field hydrogen maser. But he didn't know anything about Bose-Einstein condensation, and he didn't know much about cryogenics, so he went to talk to his colleague at MIT, Tom Graytak. And Graytak knew a lot about condensed matter and convinced Dan that Bose-Einstein condensation was really something that was quite interesting. And even though Dan realized this was going to be very difficult to do, both Dan and Tom realized this was going to be something difficult to do, they decided to set out to try to do it, and they recruited me to work on this as a postdoc. So I started working on it in 1976. I did not get very far. Others, Harold Hess, along with Dan and Graytak, were honored at the biannual Bose-Einstein condensation conference with a prize for their work in this area. These are the reasons why they got so excited about doing this with hydrogen. The interatomic potential was well known two hydrogen atoms, and as a result of understanding that potential, it was known that you could not form molecules. So this, of course, would be the first step in making an ordinary phase transition. But the fact that you could not form molecules implied, and you could calculate that that this gas of spin polarized hydrogen would be a gas all the way down to absolute zero. The gas is nearly ideal because the scattering cross section is small. The hydrogen atom is the lightest atom, so in a certain sense, it's the most quantum, and it means that you wouldn't have to get the temperature as low or the density as high as would be the case with a heavier atom. So these were all reasons why, at the time, we thought it was a good idea to do this with hydrogen. It turns out that it's not, and we'll go into that in a little bit more detail. But nevertheless, I started working on this project in 1976. I worked on it for 2 years before I went to NIST and got essentially nowhere. It became clear that putting hydrogen in some kind of a material bottle was going to lead to recombination into molecules on the surface. It's not happening in the gas, but it happens on the surface. And other things were tried, like superfluid helium coating the surface. That also was not a very good result. And what it meant was, what was understood by this group after I left, was that the right way to do this was to use magnetic trapping. And of course, this is where the work of Vanderlei-Bagnato comes in as well, understanding how magnetic trapping, or any kind of trapping, changes Bose-Einstein condensation was a very important discovery. Because of all of the things that were discovered in the Kleppner group, Dan is often called the godfather of Bose-Einstein condensation, because it was in this group of Dan Kleppner that some of the key concepts that made it possible for Bose condensation of an atomic gas to happen. It was in Dan's group that these things were developed. The idea of magnetic trapping as the way to do Bose condensation, and even more importantly, the idea of evaporative cooling, which we're going to talk about in a moment. But I want to take just a moment to reflect a little bit more on Dan Kleppner. He's not only the godfather of Bose condensation. I really see Dan as representing the soul of atomic and molecular and optical physics. Many people who come to AMO physics, atomic, molecular, and optical physics, from other areas of physics, remark on how much of a cooperative community we have in this field. And I believe that that is true, and I believe that the reason it is true is because we've been influenced by the personal example of people like Dan Kleppner. And Dan was influenced in the same way by his thesis advisor, Norman Ramsey. I think that in Europe, that people were influenced by Alfred Kastler, especially Claude Cohen-Tanucci, as a student of Kastler, exhibited these same features. And of course, it's no accident that Dan and Claude were very good friends, because they both exemplified these so valuable features of collegiality, of cooperation, of openness and scientific honesty. And it's for me, has been so important for me in my in the way that I've developed as a scientist and as a person. I have Dan Kleppner to thank for that, and I think that as a community as a whole, we all have to thank Dan Kleppner for that. Well, anyway, when I went to NIST after working on the Bose condensation of hydrogen for 2 years, along with some other things, I began to work on laser cooling. And as Dan mentioned in his the video that we've seen, laser cooling was one of the ways that Bose condensation was finally achieved by others. He was working on achieving Bose condensation by more classic means of refrigeration, like dilution refrigerators, but it was finally achieved uh, in 1995 using laser cooling. Well, I think it's probably not such a good idea to talk about laser cooling very much. I'll just point out that the idea of laser cooling came from Wineland and Daymelt and Hench and Shallow, and they all got Nobel Prizes for something else. But while laser cooling was a good start, it didn't get a gas of atoms cold enough and dense enough to see Bose-Einstein condensation. The phase space density, while much better than the kind of ordinary gases you might have around room temperature, was still several orders of magnitude too small to achieve Bose condensation, in spite of discoveries like subdoppler laser cooling and magneto-optical trapping invented by Jean Dalibard, an example of which we see here. That little dot in the middle is a cloud of atoms, extremely cold, just microkelvin temperatures with densities that are on the order of perhaps 10 to the 11th per cubic centimeter, still not cold enough, not dense enough to have Bose condensation. And in addition, there were a lot of people who thought you would never get Bose condensation with things like rubidium and sodium, because contrary to the situation in hydrogen, rubidium and sodium can form molecules even when the electron spins are aligned. And people claimed that this would make Bose condensation impossible, and that was completely wrong. And the heroes of Bose condensation, Eric Cornell and Carl Wyman and Wolfgang Ketterle and their colleagues, understood that we could in fact achieve Bose condensation in spite of the fact that you can form molecules. Now, why is that? Well, if you have a collision of two atoms, as we see here on the left, if that's all there is if just those two atoms isolated, then they will collide and they will separate and they will not form a molecule. In order to conserve both energy and momentum, and form a molecule, you need a third body, as you see here on the right. Two atoms colliding in the presence of a third atom can give up some energy and momentum to that third body and form a bound state. Now, the trouble is that in order for that to happen, or the good thing, I should say, in order for that to happen, you need to have, when two atoms collide, you need to have another atom being in the same place. And this is not going to happen very often when the density of the gas is low. The rate at which this kind of a process happens goes like the square of the density, whereas the rate at which this process happens that doesn't form molecules goes like the density. Now, if you make the density low enough, you see this process is going to be very small, even though this process can still be significant. And we need this process in order to do evaporative cooling, which we're going to talk about in a moment. Now, there are other things that can happen in collisions that are bad, even with two-body collisions, when the laser is on. So this illustrates one of the things that can happen. If I've got two ground state atoms colliding, then they've only got an attractive van der Waals potential at very close range. So it's almost as if the potential is flat as a function of the interparticle separation. You excite the atoms to an excited state. That is, so now we have one atom in the ground state, one atom in the excited state. Actually, that's an oversimplification, but now this creates an attractive potential. This creates a dipole moment, sorry about that, and the atoms attract each other and then decay, and the atoms are now going fast, and they leave the trap. So this is a bad thing, and it's one of the things that limits the density of atoms in laser cooling to a few times 10 to the 11th per cubic centimeter, which is too low. So how do you finally get it? How does it finally work? And the answer is, first, you turn off the light, at least any of the light that's resonant with the atoms, because that's going to cause these bad collisions that I've described here. You've got to now trap the atoms with something like a magnetic trap that does not heat the atoms. And as I mentioned, van der Leyen-Magnato was a key player in showing how this was going to affect Bose condensation. Now we're going to continue to cool by evaporation. And this was a really, really important contribution of Kleppner's group. Now here is one example of the, well, it's the first magnetic trap that was done in our laboratory, but it wasn't the kind of trap that could produce Bose condensation. But I don't want to go into that. It was Eric Cornell and Wolfgang Ketterle figured out ways of making a better trap, and we can talk about that during the questions if you like, but we're running out of time, so I want to get toward the important part, evaporative cooling. Now, I think you all understand the idea of evaporative cooling. If you have a cup of coffee and it's too hot to drink, then what you do is you blow on it, and what blowing on it does is it moves the humid air away so that you can evaporate water molecules from the surface of the coffee. What happens when molecules evaporate is that the most energetic of the molecules that are in the hot coffee escape from the surface of the coffee and take away more than the average energy of the molecules that are in the coffee, because it's the most energetic ones that escape. Well, we're going to do exactly the same thing with our atoms that are trapped in some kind of a magnetic trap here, and we have the most energetic atoms escape, and that means the atoms that are left behind are less energetic. So one of the things that's going to happen is, since this isn't a trap, and this is really important, the atoms that are left are going to be confined to a smaller region of space, so that even though we're throwing atoms away, the density can stay high. Another really important thing is that in order to continue this evaporation process, you've got to replenish the fast atoms that are part of the velocity distribution, and the way that happens is by elastic two-body collisions. So you've got to have lots of elastic two-body collisions, but you got to have very little in the way of three-body collisions or any other kinds of collisions that will be inelastic and will cause atoms to be lost from the condensate. We want to only lose atoms by evaporation, which is the process that cools the atoms down. So it's this balance between good and bad collisions. We want lots of good collisions, and we want very few bad collisions in order to make this thing work. And this can be achieved for rubidium, but it's very difficult to achieve it for hydrogen, which is why Bose condensation of hydrogen was so hard. Well, in spite of the fact that it was so hard, the group of Dan Kleppner and Tom Greatek finally did achieve it in 1998, 22 years after it started, 20 years after I left that group, and 3 years after it had been achieved in rubidium and in sodium. Back in 1995, it was still really hard to get rubidium and sodium, but today, getting a Bose condensation of rubidium, getting a Bose condensation of sodium, and any number of other atoms has become something easy. A standard technique of atomic, molecular, and optical physics, often used as a starting point for doing new kinds of experiments? Well, as Dan mentioned, that led to a Nobel Prize for Eric Cornell, Wolfgang Ketterle, and Carl Wyman. And let me just make a comment about what Dan also commented on in his video, that people have been talking about achieving Bose condensation for so long that it was being compared to the hunt for the Holy Grail. And as a result of that, it's when it was finally achieved, it got a lot of attention from the popular press. But not everyone in the physics community thought that it was such an important thing. In fact, at NIST in Gaithersburg, we got a visit from a condensed matter physicist who explained to us why this wonderful achievement out in the NIST laboratories in Boulder, Colorado, why it really wasn't important at all, because they'd already done it in condensed matter physics using liquid helium in an aerogel, so they were able to reduce the density and produce Bose condensation of an ideal gas, as Einstein had predicted. Well, in retrospect, that talk was quite silly, because when we look at the kinds of things that are being done today with Bose condensation that you could never do with liquid helium, it's just astounding. And just very briefly, what is a Bose condensate like? It's very much like a gas at zero temperature. It's a large number of atoms, all in the same quantum state, the lowest possible quantum state, a weakly interacting gas. It's macroscopic, both in the sense that it's got a large number of atoms, and it's a big enough cloud that you could actually see it. Young people, at least, can see things that are just 100 microns across, and that's what many of these condensates are, even sometimes even bigger than that. And the atoms can be either weakly or strongly interacting, depending upon what you want. It's a single wave function. As Dan in that little video clip that I showed indicated, the atoms sort of merge into this single wave function where all the atoms are in the same state, and it becomes a macroscopic wave function of a sort that we've never seen before. Well, there's lots of questions that I might suggest to you, but we're coming to the end of the hour, and I just want to indicate very briefly why Bose condensation has been so overwhelmingly important to not just atomic physics, but to physics in general. That with Bose condensates, we've been able to do atom optics using atoms instead of photons to do the kinds of things that you might do with light. And one of those things is atom interferometry. We can now make devices in which the atom waves interfere with one another and allow us to make measurements that are difficult or impossible to do with light. We can do nonlinear atom optics because of the fact that Bose condensates are, in a certain sense, atom lasers. That is, they are to atoms what lasers are to photons. We can simulate the behavior of things like electrons moving through a lattice of positive ions as they do in crystals. We can simulate that process by having cold Bose condensed atoms move through an optical lattice, an array of micro traps formed by the interference of laser beams, and we can simulate the kind of behavior that occurs for electrons in solids, but in a circumstance where we can make measurements and we can have control that's not possible to do for electrons in solids. We can use atoms created by Bose condensates for quantum information, for quantum bits, qubits, for doing things like quantum computing and quantum information processing. Because of the fact that it's really important to have those atomic qubits in a well-defined quantum state, and the Bose condensate is the ideal place to start with something that is a very well-defined quantum state. We can create quantum simulations where we make it appear that neutral atoms are moving in a magnetic field in the way that a charged particle would move in a magnetic field, and then do quantum simulations of, for example, electrons in a two-dimensional electron gas, having control and measurement that isn't possible for the actual electron system. So I could go on about the things that Bose condensates can do, but what I want to emphasize is that the things that were going on 100 years ago changed everything. When it came to the discovery of quantum statistics and how that led Einstein to his prediction of what we call Bose-Einstein condensation, that Bose's paper set in motion the kind of activity that we now have today in dominating atomic, molecular, and optical physics in ways that have influenced other fields of physics as well, not just condensed matter physics, but nuclear physics and particle physics as well. And so these new insights that have come from the understanding that in quantum mechanics we have a completely different approach to statistical physics has had such a wide-ranging influence on physics that it's certainly something well worth celebrating, but more importantly, something that's well worth pursuing and learning more about. And so we come to the end, but of course, it's not really the end because there's always something new to learn. Thanks very much.
Bill, thank you very much. Do you have further questions from the audience? Yes.
Well, I have a lot of questions, but I think I will start only with 3 questions. And well, I'm choosing it, so just a second, please. So my first one is historical. Bose sent the letter to Einstein, and then what happened to Bose? Because well, I don't see this name much in other areas of physics.
Yeah, so Bose seems to be what in music we would call a one-hit wonder. Somebody who writes a song and it becomes #1, and then you never have another great song from them. They produce other things, but they never achieve the same kind of status as that one amazing song that they once created. And Bose seems to be of that sort. There are plenty of other examples in physics of people who did something that really changed everything about the way we do things, but that was all. So that seems to have been have been the case with Bose.
Oh.
Do we have? I come back.
Hello again, Bill. Just another curiosity here, but could you tell us what were you doing when you had the idea that gave you the Nobel Prize?
Well, the thing about the Nobel Prize for laser cooling, it was not something where there was one idea that popped into my mind. Maybe that was what was happening with people like Ted Hench and Art Shallow, that it popped into their mind the idea of laser cooling. I had the advantage that I already knew about laser cooling, or at least about the idea, and the question was how to put it into practice. So the Nobel Prize for laser cooling to Steve Chu and Claude Cohen-Tanuji and myself was really for the development that happened over a number of years to bring the basic ideas into experimental reality, and then also the accidental discovery of different ways of doing laser cooling that were not covered by the original ideas, but that were accidentally discovered and then explained. So it was not a eureka moment, so to speak. It was more a matter of lots of hard work over a long period of time.
Bill, we thank you very much for the wonderful talk. And I hope the next time we can bring you here for a live talk. So thank you very much again.
It's been a pleasure. I look forward to being in San Carlos again.
So we have a short break now, and we come back in like 20 minutes. There's coffee and so on here on top. And for those following on YouTube, we come back live soon in 20 minutes. Okay. Welcome back, everyone. So we have Professor Celso Vilas Boas from the Federal University of São Carlos, which is our sister university in the city. He will talk about light, quantum light, or thermal light, I think. Quantum and thermal light on dark and bright collective states and the hidden energy in thermal light. Celso, thank you very much. Please, it's yours.
Okay, good morning, everyone. First of all, Emmanuel, thank you so much for the kind invitation, for the organization of this event. Professor Vanderlei as well. So it's a really great pleasure to be here with Professor Gerhard, collaborator of these ideas, and Ciro, also collaborator of these ideas. And today I'd like to talk about these crazy ideas. So my talk is going to be a little bit more technical, so I'm sorry for that. But I'm trying to convince you that many things that we learned about interference are wrong. So in the end, I'd like to try to convince you that we need a new theory to explain very simple experiments like double slit experiment. And the last part of my talk, I also would like to talk about the energy that is present in thermal state. So in thermal light, for instance, from lights like here or from stars, there is a huge amount of energy hidden in thermal states, in dark states. So this is the idea I'm trying to convince you. So basically, the first work is related to this paper we published this year. So basically, we reinterpreted the double-slit experiment. So as you see here, everybody says that in the constructive points, we have light amplified. In the destructive point, people say that there is no light there is no photon at those points. Our theory says that this is not the case. We have photons even in the dark spots, but in a specific state that does not couple to the matter. This is why we don't see light there. Not because the photons are not there, but because they are not able to couple the detector. It's completely different. And the second paper, the second idea I'd like to discuss with you is related to thermal states. So when we have light in thermal states, as I said, from stars, for instance, or from the lamps, this kind of light, there's no coherence between the states, the Fock states. So in principle, one should expect that in those kind of light, we couldn't have some bright or dark states because they are very quantum states. They are very entangled states. So in a very incoherent state, could we see similar effects? And the answer is quite obvious when we learn, of course. Because when we have any kind of state, we can decompose it in different bases. We can decompose in the bare basis or in the collective basis. And the dark and bright states appears in the collective basis. So writing the states, the thermal states in the collective basis, we have part of this light in bright and part of the light projected onto the dark states. And the part that is projected into the dark states do not interact with the matter. So this energy that is present in the dark states, even in thermal states, cannot interact with the detector as well. So it somehow remains hidden in the modes. So let's start. So everything that I'm going to talk here today is related to what is light. That is a very old question. People have been thinking about what is light since the Greeks, 300 years before Christ. So Leucippus, Aristotle, Euclid, many others, because they were interested in understanding how we can see things, how we can see each other. So because of that, they were trying to understand what is light. So as you know, there is a huge history about the concepts of light, but perhaps the most famous debate took place between Huygens and Newton many centuries ago. And there was a dispute between the wave and particle aspect of the light. Huygens claiming that light would be the waves. Newton claimed that light would be made by particles, the corpuscular aspect of the light. But this dispute, this discussion, basically had the first end with the experiment by Thomas Young in 1801, and later with the equations by Maxwell. Because both could prove that light has a wave equation, and in that moment, people believe that there is no aspect of particle in the light. So everybody at that moment believed that light would be only wave. But as you know, this is not the end of the history. Again, as Bill Phillips told us, there is the origin of the quantum mechanics with Planck and Einstein. And then Einstein proposed that light should be described by particles again to explain the photoelectric effect, as Bill Phillips told us. So the particle theory for light is back again. And then we started believing that particle should be both wave and particle. So depending on the experiment we do, we would see the wave aspect of light. Depending on the experiment we do, we would see the particle aspect of light. Interferences, of course, it would be a very strong signature of the wave aspect of light. On the other hand, experiment like photoelectric effect or Compton scattering would be a really true signature of the particle aspect of light. So that is, depending on the experiment we do, we could observe both aspects of the light. But mainly concerning the photoelectric experiment, as most of you probably know, Guido Beck in 1926 already showed that the photoelectric experiment could be explained without assuming the particle aspect of light. Later in 1968, Lamb and Scully formally derived the equations showing that indeed the photoelectric experiment could be explained only with the wave aspect of light. So not assuming that particle should be dual. I mean, just saying that the light should be just a wave would be enough to explain the photoelectric experiment. But then, of course, nowadays everybody believes that light is made of photons, and perhaps the most beautiful demonstration of this was carried out by Sérgio Haroche. Sérgio Haroche, the Nobel Prize in 2012, he could monitor the intensity of a field inside a microwave cavity. So starting with some intensity, he could monitor the intensity time to time. And he could see something like this. For instance, starting with an intensity around 4, after some time, the intensity goes to 3, goes to 2, goes to 1. That makes clear that we have only packages of energy in the mode, in the cavity mode. So this is, for many of us, is a true proof that light is made of packages, photons. Okay? But the argument that the light is made of photons was not accepted in the community in the beginning. Mainly, one of the guys that was against this idea was Millikan. Last year, we celebrated the 100 years of Millikan's experiment. And Millikan was really against these ideas of photons of light. Why? His argument, the last part, because it flies in the face of the truly established effects of interference. That means, in his ideas, this means that the idea of photons cannot be accepted because there is no way to explain the interference that we observe everywhere in terms of particles. Interference is a true signature of the wave aspect of something. So in this case, a true explanation of the wave aspect of light. And this is the point that we are questioning in the paper I showed you before. So let's try to understand the arguments by Millikan. In case we have a double-slit experiment, here, we have the source of light here. In this case, let's assume that we have a classical source of light, and we send a light here, and there is 2 holes here, the first slit here and the second one there. If the wave crosses the first, we will have a wave reaching the detector at some point there, with a specific wave vector k. But if the wave crosses the second slit, we would have a wave reaching the detector with a second wave vector k prime. So according to the classical theory, we would say the resulting field at some specific point would be the A1 plus A2. And in case we have a destructive interference, of course, this would be 0. This is the classical interpretation. So in case we have 0 field, no light, no photons, And then this is why we don't see the light at those points. So this can be explained in other terms. If you take the interaction between the light and the detector, the most fundamental interaction is described by the dipole interaction. And if the resulting field is 0, of course, the Hamiltonian would be 0, so there is no dynamics, there is no exchange of energy. This is clear. But what happens when we describe this in terms of a quantum version? In a quantum version, we have, if the light crosses the first slit, we would have a wave vector k, and this means a specific mode, A. If the light crosses the second slit, we would have a second mode, K prime, so a second Hilbert space, mode B, okay? So in this case, the right description of the field at any point on the screen would be psi. That means one photon could be, the photon could be in mode A. In this case, of course, there is no photon in mode B, 1, 0. But if the photon goes to the mode B, we would have 0 in A plus and 1 in B. So we would have this superposition state. This equation, this state, is not mine, it's not ours. Many other people already say that this is the right state that describes the photon at a specific point on the screen. I mean, Glauber, Walls, Scully, Zubai, Joaquim Storr from Stanford. Stanford, no, Gerhard. Joaquim is from Stanford, right? Yeah. All of them describes the state of the photon after the slits in such a way. So, and if you try to describe what's happening on the detector or on the screen, we had to take into account the interaction between the detector and the light modes. And this was described by Glauber, the Nobel Prize, the father of quantum optics. So, and the idea is the following. When we have a signal detected in the detector, one photon is destroyed, which is described by this operator A+, and one excitation is created in the detector. So this is what happens when we count one photon on a detector, right? In case we have just a single mode, let's think that we have not a double-slit experiment, but a single mode. And we are trying to measure this single mode. This operator A+ is described by the annihilation operator A. That is the annihilation operator of the harmonic oscillator, for those who remember the quantum mechanics classes. But to excite the detector, we need to destroy one excitation of the mode. And there is just one state, only one state, that is unable to excite the detector when we have just a single mode. And the state is the oops, oh my God. There is just a single state, psi equals to 0, that is the vacuum state, that is unable to excite the detector. All the other states, it doesn't matter if it's a pure state, a mixed state, all the others are able to excite the detector. So all the others can be detected. Only the vacuum state cannot be detected because there is no energy to exchange with the detector, with the atoms, and so on. But the situation changes a lot when we go to two modes or many modes. And this is the point. When we have two modes or more, the operator that describes the annihilation of one energy, one excitation in the modes is described by a superposition of operators, A plus B. And in this case, the vacuum state is again another state that is unable to excite the detector. But then appears many other states. For instance, here we have the psi 1, 0. Psi 1, 0, that is 1, 0 minus 0, 1, is a state that is unable to excite the detector. And what is the point? We have a photon now. We have one excitation in the modes, but in a specific state that cannot excite the detector. In other words, you cannot see. So the energy is there, the photon is there, but you cannot see. It's different of the standard interpretation that says that the photon is not there, the light is not there. This is the difference. And there is a huge family of dark states with 2 photons, 3 photons, any photons, and can go to infinite. So it means that it can have a huge amount of energy. When the modes are in such states, they would not be detected by us. We could not see. So, on the other hand, there are other states that couples to the atom in a stronger way. For instance, when you have just a single mode, the rate of exchange energy between the mode and the atoms is given by the coupling, and depends, of course, on the intensity of the field. So the number of photons we have. So it appears as d square root of n. So as bigger the n, the more stronger the stronger the coupling between the atom and the mode. But when you have 2 modes, instead of having g square root of n, we have g square root of 2. That means 2 modes have a stronger coupling with the matter. So it exchanges energy in a much faster way than a single mode. This is why we see more light in the bright spots. Not because there are more photons there, but because the light is scattering much more photons. It's different. So the intensity is the same, either in the bright or in the dark spots. The amount of photons, but the rate of scattering photons depends on if you are in the dark or in the bright spots. In the dark, no photon is scattered. In the bright, the photon is scattered in a much faster way. This is why we see a bright spot, much brighter than a single mode. And again, there are many bright states, depending on the number of photons we have. And they are very similar to the dark states. The difference is just a phase. So instead of having 1, 0, minus 0, 1, now we have 1, 0, plus 0, 1. And so on for the others. In all of them, we have the same energy. This is the point. If you take a specific number of photons, n, and you look at the dark state, it has any photons. If you look at the bright state, it has any photons as well. It means that the energy is the same in both. The only difference is the coupling. So this can be used to explain the double-slit experiment. Again, the state, as I said before, is described by this psi state. And if the photon goes to mode A, it acquires a phase exponential of k R1. If the photon goes to the mode B, it acquires a different phase, k prime R2. And when we have the difference of phase of these modes equals to 2n plus 1 pi, that means in classical interpretation, you usually say that this is the point where we have the destructive interference. Exactly at those points, the state is this one. So this means that in those points, we have exactly the dark state. So no coupling, no energy exchanged. We cannot see. The number of photons, 1. Oops, sorry. If you go to the other case, if the difference of phase is 2n pi, so the constructive interference, then the state becomes 1, 0 plus 0, 1. So that means the bright state. So now we explain the same way. So we can use now either the standard theory, the classical theory saying that we have a destructive or constructive interference, or the bright and dark state approach. Both describe the same pattern we see in double-slit experiment, can be equally explained by both theories. But then the question, well, if both theories explain the same way, what is the right one? Okay, but this is just for single photons. And if we have a huge amount of photons, like we do in your experiments in your labs, with a laser. A laser is basically a coherent state with many photons, not just one. In this case, we have the coherent states. If the coherent state cross the first slit, acquires a specific phase. If the coherent state cross the second, we will acquire a different phase. And then the final state will be something very complicated like this. Oops. Oops. Here. So if some delta phi, the phase difference. But interestingly, if the difference of phase is 2L pi, so when the state can be described by two coherent states in phase, classically we would say constructive interference. We can rewrite this state as a superposition of only psi n. Psi n is just the bright state. So when the coherent states are in phase, we decompose it only in bright states. There is no projection on dark states. This is why we see coherent light in those spots. The energy proportional to the number of photons we have there. In the dark spots here, that means when the difference of phase is 2L pi plus 1 times pi, we have the coherent state out of phase, and in this case, is projected onto only dark states. That is a superposition of many dark states. All of them are uncoupled to the detector. And this is why we don't see light again. Okay? So, in the end, as I said, both theories are explaining in the same way very well either the classical or our theory are explaining very well the pattern we see in the double-slit experiment. But this always happens. So how can we distinguish between the two theories? What is the right one? This was the question that Gerhard made me 5 years ago. Well, Sérgio, both theories are explaining the same way. So everybody can say that this is just interference. The classical interference can explain very well. Do you remember this, Gerhard? And then I started doing this calculation. Well, in all dark states, the resulting field, oops, again, sorry. If you calculate the resulting field, that is the electric field in mode A plus the electric field in mode B, is always 0. So in any point where we see destructive interference, the resulting field is 0. So it's classical in somehow. On the other hand, in all points where we have constructive interference, so the bright state has non-zero field. So this is why we explain the coupling. So again, everything is the same. In both theories, is the same. But now, let's take this specific state. We call upsilon state. That is the first mode in a specific superposition, 0 plus 1. And the second mode in another superposition, 0 minus 1. So they are out of phase. And the resulting field is 0. But now, classically, any classical book would say for that state, if you put a detector there, we wouldn't detect light. We wouldn't see a click. But when we apply quantum mechanics, we see that there is a coupling. And why there is a coupling? So the light can be detected if you do this experiment. And why we detect? because that state can be projected onto a dark state, another dark state with one excitation, one photon, another dark state with two photons, and this site 2,2. Site 2,2 is a bright state. It means that the epsilon state has a projection on a bright state that couples the detector. Then we can detect. So there is a difference between the two theories. These ideas, we use it to explain a very famous experiment. I usually say that people use this to say that quantum mechanics is mystic, something like that, because when you observe in which slit the photon pass, we destroy the interference pattern, right? This is what we explain. But what is the problem with this interpretation? If the photon does not go to the dark spots, when we put a detector that shows us from which slit the photon passed, but we assume that this detector is so tiny that it cannot change the wave vector of the photon. So that means introducing the detector would not modify the trajectory of the photon. But according to standard quantum mechanics, we say we introduce this detector that it does not change the wave vector, but then suddenly the photon start appearing in the dark spots. But how this could be possible if the detector does not change the momentum of the photon? So if the photon would not go to a dark spot, how a detector could move it to there without changing the momentum? For me, the only explanation is, well, quantum mechanics would be mystic. We could believe in other things. But with your interpretation, what is happening? In the bright spots, we have a state like this: 1, 0 plus 0, 0, 1, the bright state. In the dark spots, we have a similar state, 1, 0 minus 0, 1. That means the photon is going there, but is there, but we cannot see. Does not mean that the photon changing the wave vector. The photon is in both cases, in the bright and in the dark spots. When we introduce the detector could modify the state of the photon without changing the momentum. But modifying the state means would, for instance, to generate an entanglement between the mode and the observer. When this happens, the final state in the bright spots is a mixed state like this, and in the dark spots, the state would be the same. So there is no modification in the momentum of the photon, but there is a modification of the state. As quantum mechanics usually says, there is the projection. So, and this projection is enough to make the photon change the state, and now that's, oops, again, oh my God. So this state has projection on the bright state. And this is why we start seeing the photon there. Not because the photon changed the momentum, but what changed it was just the state. So there is no magic anymore. Well, can we observe such states? Can we do experiment that could observe that we have states that couple, other states that do not couple, and even the epsilon state? Well, with modes, we didn't do the experiment yet, modes of light, but we did an experiment with Professor Marcus Heinrich in Stockholm University in a trapped ion system, like Emilson is going to do here in São Carlos. So we have a two-mode system. So all the Hamiltonian, all the mathematical description is exactly the same as the one I presented you. And this is in this paper. And then we could observe, if we prepare the two modes in the bright state, we can see a faster oscillation here. If the modes I prepare in the dark state, there is no exchange of energy. And if you prepare just a single mode, it can exchange energy, but in a slow way. So everything in perfect agreement with the theory. We also did the experiment with the upsilon state, and in fact, the upsilon state also couples to the detector, and we can see that there is excitation there, there is particle there. Oh, sorry. Well, everything that I showed you is relating to either one or two modes. But of course, we can extend this to many modes, many modes. And we did this, firstly analyzing not double slit experiment, but a multi-slit experiment. And most of the calculations were done by Ciro, my PhD student who is here. And in this case, appears the same pattern. But there is something very interesting in this case. When we have just two modes, we have, for any number of photons, we always have one bright and one dark state, 1-to-1. But when we go to many modes, then we still have a single bright state, but m-1 dark states. So there is a huge amount of dark modes, dark states, when you go to multi-mode case. And this is why we see many, in a multi-slit experiment, we see dark spot everywhere and just a single peak of light. And then we apply this. This is just phases, difference of phases, depending on the path. But then we apply this to time-independent phases that appears in the pulsed laser, and the explanation fits in the same way. So we can explain the pulsed laser not as a continuous of sequence of pulses, but a continuous of light in bright state, dark state, light in bright state, dark state, and so on. But this is a topic for another talk. But then the idea, what's happening when we have everything that I told you so far is related to coherent light. So like a single photon or coherent state, that's somehow very quantum states of light. But what happens when we go to thermal light? As we showed here, and thermal sources interacting with the same atom. So this is very particular, of course. I'm treating just a single atom interacting simultaneously with many modes, and all of them in thermal states. Thermal states is the state, as I said, we have from the lamps here, from the stars, from the sun, and so on. And all these ideas is in this paper here. So it's on archive. So any comment, any criticism are very, very, very welcome. Please say good words, bad words, doesn't matter. I'd like to hear from you, your opinion about this, because I believe that the results are very intriguing, and I'd like to discuss even more. So thermal state is described by this diagonal form here. So in this case, we have many modes described by the same A+ operator, that in this case a sum of many, many, many modes. And the state of the modes is, the state of the modes is a product state. So there is no coherence, it's a very classical field. So in this case, we can describe everything in terms of the bare modes. So the annihilation operator of the first mode, and annihilation operator of the second mode, and so on. Or you can do a change of bases and go to the collective bases. In the collective bases, we have the capital A 0, capital A 1, and so on. And we can connect both bases through a unitary transformation. Very simple one. So in this case, what is interesting? We have a single symmetric mode and m-1 anti-symmetric modes. And the Hamiltonian, we can rewrite the Hamiltonian not in terms of the bare bases, but in terms of the new bases, the collective bases. And what is interesting is that in the collective bases, only the symmetric mode is coupled to the atom. That means if we have excitations, photons, in the other modes, in the anti-symmetric modes, they will not be coupled to the atom. And this is the point. Only when we have projection onto the symmetric mode, we would have interaction. That, in other words, only when we have bright state in the collective modes, we would have interaction. Otherwise, no energy would be exchanged. So just to give you a simple example with two modes. The symmetric mode would be A1 plus A2, and the anti-symmetric would be A1 minus A2. And the number of photons, or the number of particles in the symmetric mode can be calculated using the N0 here. And the number of photons in the anti-symmetric, so in the dark states, can be calculated using this collective operator. So taking the state, the thermal state of light, the average value of the number of photons in the symmetric mode is given by this expression, and the photons in the anti-symmetric by this one. They are very similar. The difference is just this minus here. But for thermal states, they are 0, because there is no coherence. No coherence. Those terms, A1 times A2 plus, and so on, those terms, when we take the average value of them, they are 0. So it doesn't matter those points. So in the end, the number of photons in the symmetric mode is exactly the same as the number of photons we have in the anti-symmetric mode. So it's half of the energy is in the bright states, half of the energy is in the dark states. So half of the energy cannot interact, even when they are in the thermal light. If you go to many modes, M modes, something similar appears. In the symmetric modes, we have the total energy would be proportional to the number of photons in that mode, and the total energy in the rest of the modes, in the dark state, would be m-1 times n, the average number of photons. That means we have a huge amount of energy in dark states. Okay? So the vast majority of the energy, in fact, from the light, thermal light, would be hidden for us, for the interaction with the detector with us. And this is the simulation we performed, considering exactly this situation. Many modes in thermal state, thermal light, interact with just a single atom. Of course, it's a very particular case, I agree. But we have just a single atom interact with this M mode. And then the atom can absorb the energy, and then can scatter this light for outside. So in this case, we just need to solve a master equation, Dennis-Cummings model, very simple one. And when we have just a single mode, the energy will be absorbed by the atom until the total energy be absorbed. That means if we have just a single mode, all the energy will be absorbed by the atom. But in case we have two modes, only half of the energy would be absorbed by the atom. The rest of the energy would remain there, hidden, dark for the atom. But then if you go to 2/3 of the energy remains in dark. If you go to 100 modes, basically 99% of the energy remains in dark states. We cannot see, we cannot interact. How could we observe this? Well, now I invite Gerhard. He has exactly this, this system, a cross-cavity system. We could put just a single atom in the middle of the cavity. If you prepare the modes in thermal states, the atom would absorb only half of the initial energy of the modes. After some time, we can move the cavity, or more easily, we could move the atom, changing the position of the atom, and put it in a place that can interact only with one of the modes. Because if there is energy in that mode, in the new position, the atom would absorb energy again. And we perform this simulation, this is the case. So when the atom is exactly in the middle, we see that the energy could be absorbed by the atom until half of the energy. So, and then it remains there. If you move the atom and put to interact just with one of the modes, and then the energy would be absorbed. So in this case, we could see the hidden energy there. Okay, how much time I have? 15? Okay, I have the opportunity to tell some other crazy things. Well, this is an important discussion we have in the paper, that is the difference between intensity of light and energy. And what is the point? If you take any textbooks, for instance, Jackson, Loudon, many of textbooks, they explicitly say that intensity is energy divided by area and time. So the power divided by area. Okay? By time, by area. That means that if there is energy, there is intensity. If there is intensity, there is energy. So in case we detect zero intensity, means that there is no energy. Right? This is what we find in many textbooks. And this is, I assume by myself only, but I know that Gerhard agrees with this. This is wrong. I mean, this is the standard definition, but when we go to the quantum version, the definition of intensity by Glauber, the intensity is defined as A minus times A plus, the average value of this operator. Okay, this is the definition we find in the papers by Glauber, the Nobel Prize. But let's take a simple example, a single photon case. If a single photon case state is in a single mode, the intensity is 1. Very natural, as expected. But if we have the same single photon, but now shared by 2 modes, but if it's in the bright state, the intensity is 2. So the intensity is higher than the energy. Change it. If you go to 2 modes, again, the same photon, but in a dark state, the intensity is 0. So we are always talk about the same photon, but in different states. Depending on the state, it can have the intensity 1, as expected, 2, it's a little bit crazy, or even more crazy, 0. So this is, for me, it's clear that intensity, there is also the mixed state. If you have a mixed state, like in thermal light, the intensity would be 1 again. So intensity as defined by Glauber is not the same intensity as defined by the classical electrodynamics. This is the point, and this is the confusion. Okay? So, in my opinion, intensity, according to Glauber, should be defined as energy times coupling divided by area and time. So we have to include the coupling, because depending on the coupling, we have different results. But this does not appear in the papers, in the textbooks. Well, I don't know. If perhaps Vanderlei knows this, you can talk this later. Okay? I have a few minutes. So let's go to this part. So the last one, before the thanks. Let's go back to the Planck distribution. Because in Planck, we assume that we have such a curve, and we have the total energy. We can integrate the density of energy, and then we reach the energy proportion to T4, so the standard one. But what is the point here? This curve here, this line, is the density of modes. That means for a specific frequency, we have many, many modes. So we are in the case I will discuss with you. So the case where we have many modes interact with the same atom, for instance. Okay? It's not just a single mode interact. So these collective effects must appear in those kind of experiments. So, but as I showed you, when we have many modes, only the symmetric one couples the detector, the atoms. All the others remain in dark state. So instead of calculating the total energy using this density of modes, we could calculate this other one using just a single mode interacting with the detector. Okay? And in this case, we would have a different total energy, not t to the fourth, but to the t to the power of 2. If you take the temperature of stars, the average temperature of stars, that is 3,500 kelvins, this would mean that we have a difference of energy. The total energy that is really present in the radiation, and the energy that can be detected. And there is a difference. And the difference is around 3,000 times. Coincidentally, I'm not claiming that this is an explanation of dark energy. So let me do this disclaimer here. But it's a very interesting coincidence that is this 3,000 times is more or less the difference between the background radiation we detect and the dark energy many cosmological models predict. So there is a very nice coincidence. I have no experience in dark energy, cosmological models, and so on. So this is why I cannot claim that this is really an explanation of dark energy. So let's be careful with this. But it's very interesting that it gives the same ratio. And thank you.
Thank you, Celso. Do we have questions?
Many questions.
Yeah, actually, I have many questions, and nothing has been pre-arranged. Can you go back to your last slide? Not the black body background energy dark matter, but the one before. You emphasize the coupling when you compare with Glauber's.
Okay, it's here.
You emphasize the coupling, and I perfectly agree. So the coupling means or relates to the Hamiltonian somehow.
Yes,
that
exactly.
is the business. And this is a James Cummings Hamiltonian, basically saying we absorb a photon and the detector goes to the excited state.
Yes.
We can, in principle, design different detectors. We can design, I don't know, a detector which emits a photon when triggered by a photon, for example. Or we can think about quantum non-demolition detectors, which maybe scale like A daggers A or something, which does count. So in principle, we are free to choose. As
Yes.
a theoretician, you are free to choose, so to say,
Yes.
the coupling. So how much of what you showed to us, beautiful work, of course, how much of this depends on the exact choice of this Hamiltonian?
Oh, in
The
a
dark, and,
sense,
the dark and bright state. Do they stay dark and bright if I have a different detector coupling, for example?
but in the end, we have to describe the interaction between the detector and the modes. In the end, we have to go to the fundamental interaction. And this is the fundamental interaction. The non-demolition detection, for instance, is just the case where we have a strong detuning between the detector and the modes. And then there is no absorption, but there is the interaction that is governed by this interaction. And in the end, I derived this, or already derived this.
Yeah, but I'm sorry, maybe I wasn't clear. We don't have to build a detector which is based on, I don't know, rotating wave approximation, etc.
Okay.
We can design whatever we want. As a theorist, you can write down any Hamiltonian more or less, unless it's violating some unitarity.
Okay.
Or whatever.
Of course, the pattern will change. And this is what we observed in Stockholm with Marcus. Because we put the atom, interact with both modes simultaneously, and in dark state, no interaction happened. No energy was exchanged. But then we changed the interaction between the atom and the modes. In that case, we were able to turn off the interaction with one mode and keep the other one on. And in this case, the interaction appears again. So if you are able to engineer a different detector,
So does
we
that,
would see something different.
so does that experiment involve a different detection Hamiltonian?
Yes. Changing the,
Effectively?
yes, in the end depends on the Hamiltonian that describes the interaction between the modes and the detector. This is true. And this is in my opinion, well, this is the innovation of this work. We are introducing the detector in the history. All the description of the interaction with the detector. Underlay.
No, I think it's very nice, and I think you have I saw this already in the paper. You have a paper, right? On the dark part.
Yeah.
Yeah. Okay. Fine. So,
But it's not published yet.
yeah, but it's in the
Uh,
you mentioned in the archive, right?
Yes, it's on archive.
Now, all the intensity and stuff we use is based on the point vector, because that's the way we make the derivation, right?
Yes.
Based on the density of energy and associate with the amplitude square, the intensity, and so on.
Yes, I agree.
Okay. Can we adapt the equivalent of the Poynting vector so there is no confusion and we can accommodate both things?
I think so because
Because the calculation you do is a little different, right? From
but in the
consider
end,
the propagation, free photons propagating and everything.
yeah, but in the end, here. This is not my theory. It's not our theory. This is Glauber's theory. He explained the detection process in terms of this Hamiltonian. So the point that is missing, in my opinion, is the coupling in E. We should include the coupling in order to accommodate.
Yeah, but if I have an electromagnetic field somehow, in terms of photons or amplitude of field, I can always define the flux of energy and everything. So
Yes.
my question is, can we adapt what we learn in Jackson to accommodate the coupling and accommodating that situation that you place it?
In my opinion, there are two things. One is the field itself. That is this vector pointing, the flux of energy.
Yeah, but that's the way we define it. But maybe the confusion is there.
I don't think so. The confusion is the measuring process. Because Glauber introduced the measuring process, introduced this operator, A+, that do not accommodate the coupling. So there are some states that do not couple. So the intensity we measure is not exactly the energy.
No, I understand your situation. Can I generalize this?
Yeah, probably. I have to think more about this, but
Further questions? Yes. Thanks also for the nice
Crazy.
overview. Yeah, but it kinds me like a bit of confusion about this kind of detector. If you don't put the detector there, you mean like you don't have any interference, or you still have a superposition of these? Because, for example, does it mean that this the same experiment we are seeing here will change the results if you change the detector? Or if you don't put the detector, you'd never expect any interference or any fringes?
I mean, if you put just a screen, it
Yeah.
already works out as a detector, right?
Yeah, but I
If you
mean,
put
like, if you put a detector that is classic and you don't choose any detector, so you just put a paper or a camera or whatever, it has a different interaction or not. It doesn't scatter some photons or they absorb.
All these materials you mentioned are made of atoms, and the fundamental interaction would be the same, so the pattern would be the same. It works out as a detector in the end.
And
The paper works out as a detector.
Okay. And for example, when you say like the dark mode, actually, is it the superposition of two? And it, for example, if you do many measurements, you have any chance, for example, like you say, like if you have two modes, like you have a superposition, you always have this probability of finding the sum of both will be one. But then you have a bright, I don't know, state, a dark state, and you don't detect one and you detect the other. But is that a probability of detecting, or any probability, or always zero be the probability to detect at zero mode?
In the dark spots, we cannot detect. So the probability of detecting there is zero. Okay. So I believe that a way to prove in the double slit experiment is if you put detectors everywhere, when there is just a single mode, we would always detect the photon. So if you send 100 photons, 100 photons would be detected. But in case we have two slits, part of the photons goes to the bright spots, part goes to the dark spots. The dark spots is not detected. So it means that if you send 100 photons, perhaps, I'm not 100% convinced of that, but perhaps only half of the photons would be detected. So this perhaps should be a way to certify that this is true for double slit experiment. So, but the probability of detecting photon in the dark spot is zero. So this is equal to Feynman's prediction, equals to the classical prediction. So, but this is why we are thinking how to measure everything here. Yeah. But the photo is there. It's like, imagine that you have two photos, one up and another down. Both are there, but the resulting field is zero. So this is different of vacuum. This is the point.
First of all, thank you for the talk. So I would like to ask if you think this kind of model will have large consequences on the decoherence model in quantum computers.
In fact, the dark states is very well related to the coherence-free subspace. In fact, this kind of dark state appears everywhere already. We have a paper together about the electromagnetically induced transparency. So why we send two lasers to the same atom, same atomic sample, and they do not absorb the light from the fields. Why? Because they are in a dark state, in a state that do not interact. So dark states, people have been studying them since, I don't know, 30 years ago. or even more. So experimentally. So the point is that those dark states do not interact, so you cannot see. I don't know if I answered you. Okay. Sorry.
Oh, thank you, also for your nice talk. It's a question that occurred to me when you were answering the question previous. You were saying that if you count the photons before they achieve the two slits, and you count the photons after they achieve the detector, then this, I would say, this non-conservation of energy would be, for example, a signal that your theory or your interpretation is correct. Is that?
Yes.
Okay.
Because if you send 100 photons, half of them would go to the dark spots. So they would be there, but in an undetectable state. So in this case, we would lose half of them. But I'm not sure. We already tried to do something related to this, but then appears many other details. Yes. Yes, I agree. Uh-huh.
Okay. Celso, thank you again. And we'll be back after lunch at 2 p.m.
Okay.
Thank you.
Thank you.